Hello electronics students. In this video I'm going to use a homebrew stepwise 9-volt battery supplied power supply, DC of course, to supply the voltage to a series diode. This is a 4N001 rectifying diode in series with a 100 ohm resistor. I'm going to supply this very simple diode resistor circuit with a variable voltage, and this is going to be variable in steps as I change it to this circuit, and then I'm going to measure the voltage drop over the circuit that I'm supplying, and I'm also going to measure the voltage drop over this resistor using these two leads. And I'm going to do that for various different applied voltages that I will effectively harvest from my 1K resistors using a different input, a different number of my 12Ks, and I'm tilting my protoboard to place my lead. So as I do that, I'm going to use the voltage drop over this 100K resistor as an indicator of the current flowing through the diode resistor series circuit. And I'm going to get an idea of what the relationship is between the voltage drop over this diode and the current that it allows to flow through it. Now, since these are in series, the same current is flowing through both. So I can measure the voltage drop over this resistor and get insight into current while measuring the voltage drop over the whole circuit. I can subtract those two signals after the fact on a spreadsheet or in a calculator, and then get the voltage drop over the diode, and I can construct a curve that tells me what the current voltage relationship is for this diode. And I can see whether or not it's linear like a resistor or if it follows some other path. So we'll have to see. So the first thing I'm going to do is energize my power supply. So I'm going to take my 9-volt battery, nominal 9 volts, and I'm going to hook it up. And so now I am flowing current between 4 of my 12K resistors and all of my 1Ks. So, and I am going to connect basically the resistor on my diode resistor circuit. I'm going to keep moving this so I'm putting them where they can be seen. I'm going to keep everything in the light. So I'm connecting this to the same ground that is the negative supply of my battery. So now this point in my diode resistor circuit is common to this point in my stepwise homebrew power supply, which is connected to the negative lead of my battery. So those are all basically zero. I could draw a circuit diagram and I would put that at basically effective ground. Okay, so I'll end up supplying my diode resistor circuit from this lead, or I'll measure from that lead, but I'll actually supply it with a variable probe that I'll use to attach to different points in my circuit. So I'll wait to connect that when I'm ready to flow some current. Now to make a measurement, I could use to make my voltage measurements, I could use my multimeter, but I would have to go back and forth and measure one signal after another, because for each different applied voltage, I want to measure the voltage over the diode resistor circuit and then over just the resistor to get the current. So I'm going to use the probes from my Picoscope as a voltmeter. So first thing I need to do for that is hook it up, and I have now made this point. I'll use my pen to point to it. This row of holes here is effectively my common, my ground. And because I'm not using the AWG for my Picoscope, I'm going to use the alligator clip to tell the Picoscope, hey, this is ground, this is zero, because otherwise it doesn't have a way to know, because it's not all being grounded to the same point through the AWG. So this is my channel A is now measuring across my entire two-component circuit here, the entire circuit, the diode and the resistor. Now, because all of the alligator clips are effectively grounded together, I don't need to connect another one. So I'm just going to connect my probe to this measurement lead, which is connected between the diode and the resistor. So these 2 points are going to give me the voltage drop over the resistor, and this point versus this point that I'm pointing to with my pen are going to give me the voltage drop over the full circuit. So my channel A on my Picoscope is measuring the full circuit voltage drop, and my channel B is measuring just the voltage drop over the resistor. So I'm going to go over to my Picoscope screen, which you should be able to see with my cursor wiggling around, and I'm going to turn on auto some signals, and they're jumping all over the place. So I'll add a trigger, auto, so now we can see some flat lines. So right now I'm not actually supplying any current to my diode resistor circuit, so we're not really seeing anything. So that's the next thing that needs to be done. So I'm going to put basically my positive DC supply here, pointing to it with my pen, which is the same place I'm measuring here. And the other end of this is going to go, I'm going to move over a little bit, it's going to go somewhere on my stepwise resistor series. So I'm going to start with the very lowest supply. So over my only one 1K resistor. So I should be supplying somewhere between 100 and 150 millivolts. And if I look over on my Picoscope, voila, I have a 50 millivolt full scale showing for my channel B, which indicates I'm not getting much voltage drop over that 100 ohm resistor. But if you take a look at the blue trace, which is the full voltage being applied to my diode resistor circuit, it's now got a 200 millivolt full scale, and it's jumped up to somewhere around 150 millivolts. So given that I'm going to want to know exact numbers, I'm going to give myself a measurement aid. So I'm going to add a measurement. So I'm going to measure for channel A, which is the full voltage over the diode and the resistor. I'm going to measure DC average, which is really what I want to know. There's no periodic signal. This isn't a time average or a peak to peak. This is just DC. I got a battery, it's DC. And I'm going to do the same thing for channel B. Channel B, DC average. Okay. And I'm just going to change the appearance of the screen. So my cursor is now circling the area of interest here where it says value. And if you look under value, it's a little bit small, but if you look under value for our DC average on our channel A, you can see it says 145.8 millivolts. So that's what we're applying across the diode 100 ohm resistor series circuit. Now I want to keep track of that because even though I am not really seeing any consistent signal over channel B, it's kind of jumping around between negative microvolts, so we can assume it's really effectively zero. I want to keep track of what these two numbers are each time I change the applied voltage that's going to be picked up with my channel A blue trace. So given that I'm going to want to make a plot, I'm going to pull up my Excel spreadsheet, and I'm just going to start entering numbers. And as you can see, I've set this up so I can measure 3 different diodes, but we're going to focus on these squares. They're already set up to auto-populate a graph, and I'm going to input V applied, which is the voltage I'm applying to my diode 100 ohm resistor little series circuit, and then the voltage drop that I measure on my Picoscope channel B over my 100 ohm resistor. So if I go back to my Picoscope, I can say, okay, I have 140, we'll call it round up to 146 millivolts being dropped over channel A, and we got to pretty much call it 0 over channel B. So my V applied is 146 times 10 to the minus 3, and we're going to say we got 0 over our 100 ohm resistor. So let's give it a little more voltage. So I'm going to change the position where I'm supplying. I'm going to basically look at the voltage drop over several resistors. So now I'm supplying, I'm circling with my cursor, I just highlighted it in blue. Now I'm supplying about 396 millivolts, and if I look at channel B, it's not going negative anymore. It's actually showing a consistent value. So there's some current going through, so we are getting some voltage drop over that resistor now. So we can say we're getting about 396 millivolts applied. So we're going to do 0.396, and I'm getting about 1.4, oops, voltage drop, 0.0014. Actually, this is easier to use scientific notation. I'm getting about 1.4 millivolts, so 10 to the minus 3. That makes it easier. Okay, so I'm going to look again. I'm going to leapfrog three more resistors on my stepwise power supply. So I'm taking a little bit bigger steps here. So now my total voltage drop over my circuit is 0.467. So I'll record that number, 0.467, and that's volts. So we're almost up to a half a volt, and the voltage drop over my resistor is about 7.5 millivolts. So that's real, and it's not jumping around. That's a fairly believable number. Okay, so let's give it another bump up. This time I'm only going to increase by one resistor level. So now I'm up to about 476 millivolts. 0.476, and I'm up to 8.9 voltage drop over my resistor. E to the minus 3. So, oops, let's put that in the right place. 8.9 times 10 to the minus 3. There we go. And Excel is rounding up. Okay, let's take another step. Let's take another 2 steps. So 2 more steps. I'm getting, as you can see, I'm getting close to the end. So I'm going to end up having to change this position and give each of these steps a bigger voltage drop and go back. But we'll take this value. We have 486 millivolts voltage drop over my series circuit, so 0.486 volts, and that resulted in a 10.8 millivolt voltage drop over my 100 ohm resistor. So 10.8 times 10 to the minus 3. Okay, so looking back at my protoboard, I'm practically to the end. I can take one more step, and I am now supplying the voltage drop of all of these 1K resistors, given the amount of current flowing through, limited by these 1, 2, 3, 4, 5 12K resistors that I've included in my series circuit. So I'm going to use that point, and then I'm going to go back and change this connection, flow a little more current through the circuit, make the steps bigger, and give myself a bigger supply into my diode circuit. But we'll take this number. So we have 493 millivolts, so 0.493. And that resulted in about a 12.4 millivolt drop. 12.4 times 10 to the minus 3 millivolt drop over my series resistor, my 100 ohm resistor. Okay, so now I need a little more current. So the first thing I'm going to do is move this connection back to where I'm only leapfrogging. I am only connecting over one of these 100K resistors. keep needing to move where we have some light and can see this. So now I'm going to change this position such that I'm only including 3 of these 12K resistors, so that would be in hole number 10. And you can see that gave me 183 millivolts. Now, where did I end before? I ended with almost half a volt. So I'm going to advance this to the point where this value here is just over a half a volt. So let's try adjusting. Oops! Now I got a channel overage. The Picoscope needed to rescale channel A to accommodate the higher voltage and give me a good number. So I'm going to go one more, get a little bit more than a half. 496, a little more even. Okay, 5.01, so just over a half a volt. So we'll record that one. 0.501. And we have 14.5 millivolts voltage drop over our series resistor. It's 3 in our diode circuit. Okay, so I'm going to bypass all but 2 of my, put this where I can see, all but 2 of my 12K resistors. So now rather than having 5 of them, I only have 2, so I only have 24 K over on this side. So I have a lot more current flowing through each one of these 1K resistors. So let's see, we'll go back up to the middle. My position, we're getting, the Picoscope is wanting to rescale again. So now I have 519 millivolts, so I can take that and we can see we have 19 millivolts dropped over our series resistor. So we have 0.519 and 19.4, I think it was, millivolts. So let's march up a couple, bypass 2 more, do a couple of more here. So now we have 540 millivolts being applied, 0.54, 543, 54 flat, 540, and that resulted in about 27 millivolts drop over the resistor, 27 times 10 to the minus 3. Okay, let's bypass another of our 12K resistors and see if we can give ourselves a little bit more voltage drop. I'll let the Picoscope rescale. Okay, so now we're at 589, 590, so 0.59, 0.590 being applied to my diode, and that's resulting in 46.3 millivolts drop over that series resistor. 46.3 is 10 to the minus 3. And so basically this is a little bit tedious, but we're just going to keep going. So I'm going to jump where we've bypassed most of those. So now I'm supplying 613 millivolts, and I'm getting 61 millivolts drop. 0.613 and 61 times 10 to the minus 3. So back I go. So now I'm going to bypass all of my 12K resistors, so I'm going to flow current directly from the battery only through the 1K resistors. So that's going to give me quite a bit of voltage drop per 1K resistor. So I'm going to plug back in and see what I get. I'm now looking at the voltage drop over only 4 of those 1K resistors, and because I got a lot more current flowing through them, that's giving me a 675 millivolt drop, and that's a higher number, 675. And what is that giving me on channel B? Almost 98 millivolts. -3. And so we'll keep going up, supply a bit more. So now we're supplying 743 millivolts to our circuit. And we're getting 147 millivolts voltage drop. I don't have to use scientific notation anymore. And I'm going to go from auto to, I'm going to kind of make sure I changed my scale to a large fixed scale so the Picoscope wouldn't have to keep rescaling and running into its auto scale error. Okay, so now I'm giving 875 millivolts to my diode circuit and getting 250 millivolts voltage drop over my series resistor. Okay, so 875, I don't remember what these numbers are, 0.875 and 251, 0.251. And we'll do maybe one more, not quite the maximum. So 1.4. Woo. So 1.4 volts and on the full circuit. That was quite a jump. And that results in 716 millivolt voltage drop over the series resistor, so 0.716. Okay, at this point I'm going to disconnect the effective power supply to my my diode resistor series circuit, and I'm going to unhook my battery so I'm not depleting it. And at this point I'm going to turn my attention totally to my Excel spreadsheet. So at this point what I need to do is do a couple of conversions and then see what the plot looks like on my table. The table, or excuse me, my chart. My chart should be drawing from these two columns that I haven't filled in yet. So what I'm going to do is I'm going to populate them by calculating what they are. So this column, the I in milliamps, is effectively the current that's flowing through both the diode and the 100 ohm resistor. So I know what the resistor value is, I know the voltage drop over it, I can get the current flowing through it by Ohm's law. So, and because I'm going to express it in milliamps, I'm going to multiply by 1,000, so I'll start with that. Times current is voltage, and the voltage I care about is coming from that square, divided by the resistance, which I know is 100 ohms. So that gave me a 0. And I'm going to use my spreadsheet to copy that down for each one of those squares. So that's going to give me current for each one. So you can see as we apply more voltage to the circuit, we get more current, but not sure it's going to be linear, which would be the case if this were just a resistor. Okay. Second, we're going to calculate the voltage drop over the diode, and to do that all we have to do is remember that the diode and the 100 ohm resistor are in series, so the V applied is being applied to both. They form their own little voltage divider, so all I have to do is subtract V applied and V over the 100 ohms, and I now see one data point. So I know that I properly set up my chart to auto-populate, and voila! So I now have the current voltage relationship for this particular diode. So let's take a look. I'm going to move this chart over to the middle of my screen and blow it up a little bit. So we have applied voltage on the x-axis. Just move the label down, and we have, actually, this is the wrong label. I've improved this. This is actually the current flowing through the diode. Diode current in milliamps. Always important to label your axes so you know what you're looking at. So let's look at how that compared to our numbers. Yep, we max out at 7 milliamps. We started with 0. So we're drawing from the right part of our spreadsheet. Okay, so if we were looking at a resistor, this would be a straight line. V equals IR. That's a line equation basically. What we're seeing is that below a certain applied voltage, which is somewhere in here, 0.5, 0.6, we really don't get much of anything. And down here, certainly below 0.4, we got negligible current flowing through the diode. It was as if it were an open. But when we get somewhere above 0.6, certainly 0.7, had we kept going, we would have noticed that this line becomes almost vertical, as if it's a short. So that's consistent with what we know about diode behavior, and most importantly, the forward bias voltage of a diode. So we know that for a typical silicon rectifier diode, which this is, the forward bias voltage is somewhere between 0.5 and 0.7, depending on what threshold of current flow we're using to define it. So if we define, say, 2 milliamps of current flow in the case of this circuit, we would say our turn-on voltage was somewhere around 0.6 volts. And we could define it, if we wanted to define it higher, up here where our current flow is limited almost exclusively by the resistor, we would define it closer to 0.7. Now, something important to remember is in this case, we're not ever really getting a straight vertical line like we would if we just had a diode. And what we're seeing as we get to this portion in the curve where we have the last few points, where we're getting something closer to a line equation, what we're seeing is that the current voltage behavior of our whole circuit is being more limited by that 100 our 100 ohm resistor. So the current flow ultimately will be controlled exclusively by the resistor. So the current flow through the diode is less than what the diode would give if it were all by itself. So if I wanted to more accurately assess just the diode behavior, I would have used a smaller resistor, which would function as a true shunt resistor. This one was a little bit on the big side, and therefore it is effectively altering the measurement circuit because it's providing resistance that above the forward bias voltage, it's controlling the current. So I have to accept that I'm not going to get a totally accurate view of what my forward bias voltage is, but I do facilitate my voltage drop measurement for these fairly small currents that I'm using. Nonetheless, I can definitely see that I don't have a linear relationship with the diode, and I know that my forward bias voltage is somewhere between 5.5 and 7, which is very characteristic for the type of diode that I'm using. And that above it, if I continue to take more points, I should get a straight line with a slope that would indicate 100 ohms or 1 over 100 ohms current versus voltage. So it would follow Ohm's law for basically my measurement resistor. Now I can continue this by using other diodes. And in fact, I would highly encourage you to make your own spreadsheet and create your own diode current versus applied voltage plot. See how it changes. You get the benefit of seeing a light turn on if you use an LED. And in fact, I can swap out my rectifier diode and I can put in, say, a red LED in the same position. I'm winging it a little bit here, looking over my protoboard. putting it in the forward bias position. Hopefully, if I don't, if it's in reverse bias, it's not going to do anything. And I will try hooking my battery back up here. We're gonna use a few more of the resistors. And I'll go back to my Picoscope so we'll see what we're applying again. So I'm flowing current through, just looking back at my protoboard. See if I can get to where I can see visualizing my LED here. You'll see it better when it turns on, hopefully. So I'm going to try, I gave it 157 millivolts to the full circuit. I know that my forward bias voltage for an LED is much higher. It's, I believe, above a volt, so that's 0.7, not turning on. I gave it 1.6, not quite, maybe. So I'm going to move my power supply over. This is a little qualitative exercise. So 1 volt. Up, beginning to see some lighting up, 1.7. And there we go. Off, on. So that's reasonably high. 1.7. So that's definitely enough to turn it on. We can go a little bit higher and make it brighter. So 1.78 and off. Okay, so that's just demonstrating that when we supply a voltage that exceeds the forward bias voltage of our diode, we get current flow, and of course current flow for an LED is proportional to the light emission, so it glows brighter the more current that flows. And definitely our forward bias voltage is going to be higher for an LED than it is for our silicon rectifier voltage, our silicon rectifier diode, excuse me. If we used a germanium diode, it would have an even smaller forward bias voltage, more like 0.2, 0.3 volts as opposed to the 0.7. So each different diode, depending on its construction and type, is going to have a different characteristic forward bias voltage. That's something that you can look up on excuse me, on the data sheets. It does vary slightly with temperature and to a certain extent with current and voltage. Those are all available on your sheet. You can always construct your own curve if you want, but if you're going to do so, definitely use a lower value resistor, a true shunt resistor for that kind of measurement circuit. So that is it for this demo. So important points. First off, use of series resistors and a battery source for an impromptu but very useful functional power supply to supply DC. The note that we can use our Picoscope as a voltmeter and give us numerical values for 2 channels at the same time. And I guess if we'd needed 3, we could use the digital multimeter. So between your multimeter and your Picoscope, you can gather 3 voltage signals at once, and then remembering with our spreadsheet, remembering how to interpret our voltage drop measurements to make sure that we know what we're measuring and how to plot something meaningful in terms of current through our diode versus voltage drop over it, and at what point we need to remember that our current signal is no longer a function of our diode, and that is whenever we start to get up to where we're seeing a non-vertical line. And the higher the resistor we use in series with our diode to make this measurement, the flatter that line will be, the less characteristic the behavior will be of a pure diode. So that is it for this exercise. Please practice this. This is a lot of different fundamental electronics concepts that you can practice, and a great use of Excel spreadsheets. If that is something that you're learning, this is a great way to use electronics to practice your spreadsheet skills. So thank you.